Sorry, so I'll just wait until it starts broadcasting and I'll repeat for the stream. All right, we are over here. That is actually better. So we can say this has at most this many poles. We can also say, okay, what's the lower bound? And by the lower bound, I can just say, well, if I just count up to the point where I get to here, that's going to be the lower bound of coles. So the smaller amount of coles, it's going to be like 1 plus 2 and so on plus 4 up to 2n/2. Right? And that's just because here we have n/2 levels, because I go from n to n-2 to n-4 and so on down to 1. Right? So what's the sum of those? So from 1 to 2 to 4 and so on to 2 to the n/2. Well, that's approximately the 2 to the n/2. And this is square root of 2 to the n, because 2 to the power 1/2 is square root of 2. So this is like O of square root of 2 to the n. So this is a lower bound. It's not a complexity, not the complexity for this, because there's more coles than that. And there is at most this many, but actually less. So one estimate that you can give is, well, it's like somewhere between this and this. Now, this is not a very useful estimate. The reason this is not a very useful estimate is that there is a big difference between square root of 2 to the n and 2 to the n. Like, try plugging in like 1,000 to the 100 and well, 1,000, like 100 to the 1,000 and 10 to the 1,000. Like, those are very different numbers. Okay. So how do we do this analysis in a way that actually makes sense, where we don't get two estimates that like graphically look the same, but actually in practice are extremely different? Well, what you can say is, okay, so the function is so the function is this. So instead of doing my Cole tree approach, which gave me an upper bound that's clearly an overestimate of O of 2 to the n, I'll take a different approach. Again, this is like, it happens that it's going to work, but this is like obviously not the kind of thing that you can come up with on the exam. So I'll define the function T of n, and I'll say that's the runtime for fib n. I just defined it. I don't know what it is yet, right? And then I start thinking about, okay, so what is T of n? Well, what's the time that I need in order to compute T of n? Well, it's basically the time that I need to compute this plus the time that I need to compute this. That's basically all that the Fibonacci function does, is it computes this, it computes this, there's another plus sign, but if those are floats, that's like nothing. So that means that T of n here happens to be T of n minus 1 plus t of n minus 2. Like plus epsilon, but whatever. Right? So that's just like from the logic of the function, that's true. Right? Now, this should remind you of something. It's the same formula as the formula for the Fibonacci sequence, more or less. So as it turns out, it's itself. So T of n is proportional to so the best estimate is fib of n. So that's not as weird as it seems at first, because we actually already saw this exact same phenomenon just now, right? When we did power 2, and we said return power 2 n minus 1 plus power 2 n minus 1. Well, we could also say T of n is equal to T of n minus 1 plus T of n minus 1 for those same reasons. Right? And then again, kind of with the same kind of function, because 2 to the n is equal to 2 to the n minus 1 plus 2 to the n minus 1, that was the whole idea of the recursive call. The complexity was of 2 to the n for a similar reason, right? So essentially, like, you're returning 1 here eventually, and then you're just like reproducing this. So if you can swap the t function for the name of the function, you get basically the same function as the complexity. So here, this is just like a weird curiosity. You wouldn't think about it this way. Here, it's like if you want the amount of time that fib takes, the call tree is complicated. I don't know how to compute it, right? It's hard. But you can get around it using this trick of defining the runtime as just this unknown function t, and then saying, what might this t be? All right? Make sense? So that's kind of neat. So a neater thing still is that actually the Fibonacci numbers, you can compute them this way using the recursive function, but you can use, for example, linear algebra to just derive a formula, right? That you probably didn't do it, but like you can look it up. There is a formula. The formula is so it's not approximate actually. So like formula for fib of n, it's like floor phi to the n divided by square root of 5, something like this. And phi is the golden ratio, approximately 1.61. So again, like, I'm not going to get into it because I want to do something else this lecture, but you can look it up. It's not like a difficult linear algebra thing to solve for what's fib of n, and this is going to be the answer. And that's nice because actually our estimate was for the complexity of fib of n. Well, it's more than O of square root of 2 to the n, and not as much as O of 2 to the n. And as it turns out, it's O of this much to the n. So that tracks. All right. Okay, makes sense? Questions about this? So you probably have a question in my mind. So which of those do I need to know? You do not need to memorize that, the complexity of this kind of fib. It's like more trivia than anything. So this kind of technique, doesn't always work, but I've shown it to you. It could be that there is like a question that we come up with where this is applicable. It's technically applicable to any question where the question is what's the complexity. But it, like it would, if it's there, it would be an advanced question because like, case by case, you actually, so this trick of just saying, I'll just define this T of n and I'll figure out what it is later. That's straightforward. Figuring it out might or might not be easy. And we haven't done any examples of it other than this one example. So it's kind of a case-by-case problem solving kind of thing. All right. Questions about this? All right. So in general, I know how many people attended yesterday. I know that some people got like a question about what's in the handout wrong. So you definitely weren't here, or else you were really in trouble for the handout. But in general, just like as you're reviewing for the exam, just look at the different shapes for the recursion. So for example, so for factorial event that's like this is just like, a line n -1 and -2 and so on. And then for fast exponentiation, it's like n to n over 2 and so on. And you should know that that's log 2n tol. So that's of log n. And then we had, a call tree that's like the slower power. So that's the one that we did just now. So that's of 2 to the n and so on. All right. So there's not very many of those that are common. So just like look them up and then, or you can't look them up during the exam, but you can kind of remember them. There's not very many. And then try to draw the tree for what's given to you and try to identify which way to go. It's not actually hard. I know that some people just say, okay, well, complexity, whatever. I was building the bridge, I was busy, but it's not actually very hard marks if you put in a little bit of time in just reviewing this kind of thing. So I suggest you do. All right. Questions about this? Hello. All right. So the next thing I wanted to do was kind of some of it is just going to be examples that are examples like any other example. Some of it is going to be just like a broader philosophical view of what we're doing here. I'll again mark out what's on the exam and what's not on the exam. So here's an example of a function that's really, really difficult to analyze for complexity. And we'll see why. In order to tell you about it, I need to tell you about Fermat's last theorem. So Fermat's last theorem says that for integers x, y, z, right? So for squares, obviously, like that 3 squared plus 4 squared is equal to 5 squared. That's no problem. So you can solve it. Fermat's last theorem says that for larger n's, that does not work. Make sense? So what I want to do now is, so that's been proven like 20 years ago, something like that. I think more, but like recently it wasn't proven for centuries. People didn't know whether it's true or not. Right? So what I want to do is I want to write a function that just looks for solutions to this sort of equation. So I'll name it Fermat. And I want to return integers x, y, z such that x to the n plus y to the n is equal to z to the n. That's what I want to do. Fermat's theorem says that for n3 and above, that's impossible. But maybe you don't know that, right? So how do we do that? I need to try every possible triplet, right? If there is a solution, I'll just stop. So how do I try every possible triplet? So here's a trick. This trick is called dovetailing. That's just like the name. Try all possible triplets with x, y, z all smaller than 2. And then the same, but with x, y, z smaller than 3. And then the same with x, y, z smaller than 4, and so on. Eventually, I will try all of them. So this trick allows me to try to just do a loop that tries them, right? Because before that, it was like, how do I try all the possible combinations? They all go to infinity, right? What I'm saying is, well, try everything up to 1, everything up to 2, everything up to 3, and so on. That allows me to just write a nested loop. So I'll say my max is initially, 1. And I'll say, while true, so I'll say for x in range 1 up to my max plus 1. And for y in range 1, my max plus 1. And for z in range 1, my max plus 1. If I found a solution, I'll return x, y, z. If not, I just keep going. If I'm done with this nested loop, I'll just increment my max by 1. Make sense? So that's it. I can now call it. So if I call it with like Fermat, call it with Fermat 2, it finds me the first triple where 3 squared plus 4 squared here is equal to 5 squared, 9 plus 16 is equal to 25. This is called the Pythagorean triplet because it's like the length of the sides of the right triangle that are integers. If I do something like this, and then have like a greater than equal, then that's an infinite loop. The reason I know it's an infinite loop is Fermat's last theorem says it's an infinite loop. That took hundreds of years to prove. So the point is, it looks, I'll stop. So the point is, it looks simple. It's a nested loop, but it could be that there is like extremely intricate mathematical structure there where in order to know, like if someone asks you what's the complexity of this, what you would say, well, it's trying to find counterexamples to Fermat's last theorem. It's probably not going to manage. So therefore, it's an infinite loop. But in order to know this, you would have to know a lot of math, right? So the point I'm trying to make here is it's not simple. Make sense? Right, questions about this? So what do you need to know about this? One, complexity questions can be difficult. You all know this anyway, so that's not new information. But you didn't know how difficult. Two, the technique of enumerating all the possible triples, whatever, that's like a legitimate example, right? Make sense? Questions about it? All right. So I have 13 minutes left. And in the 13 minutes that I have left, I will try to give you what I think is like it's a little bit philosophical, but also it kind of follows nicely stuff that we have been doing. And it also connects with what you've been doing in your other classes, which is like writing proofs and stuff. So first, what I'll do is I'll introduce you to the halting problem. So Alan Turing's a famous result. This is like not just difficult. You already kind of see that it's difficult for some of those things. It might be that you're being asked to prove like a famous theorem in order to know whether it's an infinite loop or not. But Alan Turing's result in the 1930s is stronger. Alan Turing proved that this is like impossible to do. There is no function that takes in f and x and is able to always correctly say, is there an infinite loop there somewhere or not? And I'm going to prove it to you. It's going to look a little bit like a trick, but it's not a trick. It's just how it works. So what I'm saying is assume that a function that does this exists. Name it Holt. So Holt would take the function f and the input x. I'm being slightly informal here, but like we saw in the lab, the f and x, they could be strings. So think of them as strings, and then if you have to run them, you can use exec, you could do, some more complicated stuff. Like the point is you are able to look inside the function, look at the text as well, and maybe you hope that way you'll know that there is an infinite loop there. What we're proving is that it's impossible. All right. So here is what we're going to do. What we're going to do is we're going to say, assume that it works. And then we're going to prove that if you assume that it works, you'll get something incoherent. So we'll say, if when I give f as the input to itself, I'm allowed to do it. They're those are all strings. I'll just write this kind of thing. All right, so I'll name this confused. And I'll have the how that's separate. Else I'll just return. Okay, so I'm assuming that this function exists. You can't actually write it. That's the whole idea. But I'm saying if you could write it, you could also write this function. And then I'll ask, okay, like this is just Python, right? So what's the output of confused of confused? Well, it turns out that it cannot be true and it cannot be true and it cannot be false. And the reason is that if confused holds when you plug confused into itself, then it also doesn't hold because it produces an infinite loop. If confused doesn't hold, then it returns. So assuming it holds produces a contradiction because you get to those lines. And assuming it doesn't hold produces contradiction. And that's because if it doesn't hold, then this is false. So you just return. So it's not supposed to hold. So neither of those produces a coherent theory. So this is just Python code. So the problem is not here. The problem was with the assumption that you can write this hold function in the first place. So we started a proof by saying, assume that you can write this function hold. And we made this function confused, which cannot return true and cannot return false because both of those produce logical contradictions. So I know I talked kind of fast through it. It's easy to insert tricks when you do this kind of thing. But that's a 100% bulletproof, rigorous proof. The function hold just does not exist. If you think about it, that's like already remarkable. What it's proved is like with math is like you cannot make a physical computer that does something. It's even though the task is well defined, it's a statement about what you can and cannot do with physics, right? You cannot build a physical computer that takes in Python code and in general correctly says whether it has an infinite loop or not. Just impossible in general. It shouldn't be extremely surprising because in order to be able to do that, you would need to be able to solve all of math, like we saw just now, right? So it's a really hard problem. So it's not extremely surprising that that's the case, but it's surprising that it's provably not the case that you can do that. So that leads to something that's even more relevant to your life. Well, not that relevant. What do you need to know out of this? Nothing. That's Gödel's incompleteness theorem. And so this is like just something that can be proved with the intellectual tools that we got in this class. So I think it's a nice place to put it. How many people heard about Gödel's incompleteness theorem? Yeah, some people. So informally, it says there are true mathematical statements that cannot be proven, like with like reasonable axioms, whatever. So it's like spiritual truth. Like there's like details that you have to specify that are kind of difficult, but that's the basic idea. And with Turing's result, that the halting problem is not in general solvable, we can actually prove it very easily. So here's what we're gonna do. We are gonna say, okay, suppose any statement can be proven. So in particular, that means that f holds on x is true can be proven, or the negation of it can be proven. Right? It's one or the other. And it must mean that, one of those is provable. But if that is true, then here's an algorithm for solving the halting problem. So all proofs is going to be like generate all proofs. generate all proofs is going to be kind of like generate all passwords, like generate all the strings. Some of it is not going to be proofs. Some of it is going to be like attempted solutions to calculus exams. Some of it will be like the full text of the Twilight novels, but some of it will be valid mathematical proofs, right? So it's possible to generate all the possible strings. And that's okay, like for proof and all proofs. So we're going to say if proof proves that f holds on X, return true. If proof proves that f does not hold on X, return false. So there's details about like how do you verify that something is a proof or not, but like that's actually doable, right? So like you specify a format in which the proofs must exist, so you can do it. So again, it was a proof by contradiction. We assumed that any statement can be proven, and using that, we said, well, like if any statement that's true can be proven, you can actually solve the halting problem. But we proved that you cannot solve the halting problem. So that means that the assumption that any statement can be proven or disproven is false. That's the only thing, right? We assume, like the only thing that we used is we assumed that anything that you say, either it's true or false. Well, it's either true or false, and separately, either you can prove it or not. But if it's the case that you can prove or not anything, then you can solve the halting problem by just enumerating all possible strings and seeing if it proves or doesn't prove f holds on X. But we proved that that's impossible. So the assumption that any statement is provable or any statement is provable or disprovable is just false. And again, no tricks. That's just like this is how math works. In any axiomatic system, there are statements that like are in some sense true, but do not have a proof. Don't try to use that excuse to get out of like the last question on calculus. But you never know. Jim Davis might come up with something. All right. Okay. So I will be seeing you. In particular, my office hours are at 6 in SF 1013. I'll announce some for tomorrow and Friday if people are still working on project 3, and then we have office hours closer to the exam, which is a couple weeks away now. All right, so I'll see you then, and then I'll see you in the new year. Good luck with the exam. Bye. Fill out the course evaluations, please, if you clap. Thank you. So, yeah. Yeah. So you got half the mark for using the Chaser AI. And then there's competition, and then there's like prizes for basically first, second, third place. And it's usually like if there's special mentions, they usually get like 1 mark on.
I know other, but I do. I know some people. I think by Andy Wiles in 1999, and I saw that. Yeah, more than I saw. You know, I just want one of those. You can take it.
Yeah.
Like your whole
Like 3 hours of sleep, so if the day goes weird, it's like. Fair enough, yeah. Okay. I made it, so, really just a small amount of points. So, to be clear, I haven't been like, out and like. So. So it's all depending on some of the. As soon as it is. Which is not a big problem. That really. Yeah.
You're getting
It should be like you're going to practice with that. This and this and.
Never seen. We will. You can see things.
Okay. Yeah. So if the target one is not, then like you say, there is a high between all the options because all the similarities are -1. So you would return the first one because of the target. If one of the options is not in the dictionary, then it's just considered -1, and then we return like it could be that the option. So if the target word doesn't exist, then it's definitely a tie. Well, yeah, because sorry, if the target word doesn't exist. If one of the target words doesn't exist, then it's not necessarily a tie. So it's just like you consider that similarity to be. No, like if the choices of which the similarity is considered, right? And that you just look at which similarity is the highest. Right. Hey,
Sir, we just had a really quick question.
alright,
So, you know how you posted like a bunch of public tests?
Yeah.
We were wondering like how we can actually run those?
yeah, so what I would suggest is not like running the whole thing, but you can look up the name of a particular test in Grayscope because they're the same.
Exactly.
Yeah.
Okay, thank you.
Yeah.
So. This is what test that I'm failing. I don't know, it's passing everything else. It's
Okay.
literally this, so I was
Okay.
trying to find the test, and
Okay,
I found like this.
sorry, I didn't catch what the name was. Normal word to
File, yeah.
Okay,
So I'm not sure, but like I have like these test cases, but I'm not sure.
like,
Like,
so look like control F normal, I guess.
like, 'cause that's. the results.
Weird. Okay,
Yeah.
could you put it down?
I'm just like, it's just
Uh,
kind of confusing, because also like, when I do it
Yeah.
on my program, which is the same one I just resubmitted it, I get the, like. Correct.
Okay,
So I'm just kind of.
okay. Oh, I see. I'm not sure it's, yeah, it's
Can you
not,
show me where to
yeah.
find the test?
yeah, so where are all the files? Oh, it's in test.
Yeah, so these are.
Yeah,
this is
yeah,
the
yeah,
test,
so
and
can you,
this-
yeah, so can you go to the test folder?
Yeah, like. There you go, like, let me just. So like,
Yeah, no, you
like,
have,
the-
you have it there.
I know, I have it. But like, I have it, so there's
Yeah, so,
Yeah.
yeah, so just find like,
whatever,
yeah, so just look through like, because like I don't know
Yeah.
where exactly it is. It's just like,
Yeah.
you just look through the Python file.
yeah. So look for the test there.
Yeah, so it's probably, I think it did say files, so it's probably.
Well, no, the
uh,
word is file, so that's the dictionary they're looking at there, but
Uh,
it's just like word count. from files, yeah.
Okay. Not comfortable on the Mac. I'll just look at